All right, now let's take what we've learned about cations and anions and put them together and start naming ionic compounds. All right, so the first thing I want to say here, I didn't actually put this in the text of the slide, but I want to emphasize that the reason we're doing this, we've been talking about nomenclature for a while, and nomenclature, of course, is naming things, and it is important to name things properly. But I want you to understand that the reason that we're doing this is not just about names. The reason that we're doing this is part of being able to name something like sodium sulfate. The reason we work on names is because it's important when you see something like this that it doesn't just look like a collection of sodiums and sulfurs and oxygens, and that when you see this, you say, okay, I see what that is. That's an ionic compound, and it's got two parts. It's got a sulfate which has a charge of 2 minus, and then stuck on that or associated with it or electrostatically attracted to it, whatever you want to say, are a couple of sodiums, right? And so being able to name this correctly as sodium sulfate is important to understanding what this actually is. And what this actually is a compound with two distinct parts to it. It's got a sulfate, which is SO4 with a 2 minus charge, and then it has two sodiums attracted to it, kind of added to it with an electrostatic attraction between the positive charge on the sodiums and the negative charge on the sulfate ions. Right? And the sulfates and the sodiums are going to behave somewhat independently. So if you take sodium sulfate and you dissolve it in water, it's going to behave as if it's a solution containing sodium ions and sulfate ions, right? So the behavior of that solution depends on the things that the ionic compound is made of. And so it's important to be able to look at a compound and recognize the different parts and understand that the behavior is going to be dependent on the behavior of those different parts. All right, so now, going back to the nomenclature, there are really two rules, and the rules are really simple, and that is that when we name ionic compounds, we just name the cation and then the anion. All right, so for example, sodium chloride, we've got sodium cations and chloride anions. And so the name of that compound is just sodium chloride. You name the cation, and then you name the anion. Right? So that's why we've been working on independently on learning how to name cations and anions. The second rule is that when you put the compound together, you have to construct it so that the net charge is 0. Right? And that means that the total positive charge is equal to the total negative charge. So when you add all of the cations and anions together, the net charge is 0. Those are really the only two things that you have to know, in addition to being able to name the cations and the anions independently. Those are really the only two things you need to know, but they do take a little bit of practice. All right, so let's go ahead and try some of these. We'll go through a couple where we start with names and get formulas, and then we'll do some where we go the other way around. All right, so let's see how we can use this to write formulas for ionic compounds based on their names. And we'll start with sodium chloride. Sodium, there's no number here in Roman numerals, nothing to tell us the charge on the sodium, but because sodium is in group 1, we know that sodium has a +1 charge. And for chloride, this IDE suffix here tells us that it is a simple anion. So it's not an oxyanion, there's no oxygens on it, it's just Cl. And if you look at the periodic table, you'll see that chlorine has one fewer electrons than argon. So chlorine, when it forms an ion, it'll add one electron to form chloride. And since the charge on sodium is +1 and chloride is -1, we can just combine them together with one sodium and one chloride. And so our formula is just NaCl. All right, now let's look at magnesium bromide. Magnesium, again, there's no Roman numeral here, but magnesium is in group 2. And so we know that magnesium has a 2+ charge. And bromide, because it ends with IDE, we know that it's a simple anion. So it's just Br. And by looking at the periodic table, we can see that bromide has a charge of -1. So now we can't combine these together the same way we did with sodium chloride because the charges aren't balanced. So I'm going to make a little table here. And this is, it's really simple. You probably don't need to make a table in most cases. But again, I want to go through the systematic approach because it might be helpful when you get to something that are more complicated. So we want to find a way to combine these so the positive charge and the negative charges cancel out. So if we look at the magnesium, one magnesium would give us a charge of +2. Two magnesiums would give us a charge of +4. 3 magnesiums would give us a charge of +6. 4 would give us a charge of +8, and so on and so forth. For the bromides, one bromide would give us a charge of -1. 2 bromides, a charge of -2. 3 bromides, a charge of -3, and 4, a charge of -4, and so on and so forth. So we see that we can combine them if we have one magnesium, we get a charge of +2, and 2 bromides, we get a charge of -2. So in order to combine these so that the charges are balanced, we need one magnesium and 2 bromides. And so we would write the formula MgBr2, meaning that the compound contains 2 bromides for every 1 magnesium. All right, now let's look at ammonium sulfate. Ammonium is one of those polyatomic cations that we learned. All right. Ammonium is a charge NH4, or excuse me, formula NH4 and a charge of +1. Sulfate is one of the oxyanions that we remembered, and that's SO4 2-. Again, we can't combine them with just one of each because the charges aren't balanced. So we'll make this little table. And 1 ammonium would give us a charge of +1. 2 ammoniums, a charge of +2. 3 ammoniums, charge of +3. 4, charge of +4, so on and so forth. For sulfates, 1 sulfate gives us a charge of -2. 2 gives us a charge of -4. 3 would be -6. 4 would be -8, and so on and so forth. And so the way we have to combine them together so that the charges balance is to have 2 ammoniums and 1 sulfate. Okay. Now when we go to write the formula, we can't do exactly the same thing that we did for magnesium bromide. For magnesium bromide, to indicate that there were 2 bromides, we just put a 2 down there as a subscript. We can't do that here with ammonium because if we do that, it looks like NH42. So anytime we want to indicate that we have more than one of a polyatomic ion, what we do is put the ion in parentheses and then put the subscript outside the parentheses. So if we write it this way, this means that we've got 2 ammoniums and 1 sulfate. And that is the correct formula for ammonium sulfate. All right, now let's look at iron 3 oxide. Now for iron, iron is a transition metal, so it can have multiple different charges. Right? But because we've got this 3 in parentheses here, we know that in this particular case, this is an iron 3 ion with a charge of +3. Right? For the oxide, this IDE suffix tells us that this is a simple anion. So it's just an oxygen with a negative charge. And if we look at the periodic table, we see that oxygen is 2 spaces away from neon. So when oxygen forms an anion, it's going to acquire 2 electrons to have a charge of -2. So if we want to combine these two, right, we look at the possible positive and negative charges. 1 iron gives us a charge of +3, 2 irons +6, +9 for 3, and +12 for 4. And for oxygen, 1 oxygen is -2, 2 oxygens -4, 3 oxygens -6, 4 oxygens -8. So if we want to combine these together so that the charges balance, we need 2 irons and 3 oxygens. And so we'd write this way. Okay. Wonderful. Okay, I want to mention something also at this point. Sometimes people tell me that they learned in school that when they're writing these formulas, just to take this number, put it over here, and take this number and put it over here. That works about 80% of the time, and you can see that would have worked here for the iron 3 oxide, but that doesn't always work. So please don't do this. Please don't do this little thing where you just swap the numbers around. Please think about what you're doing, and even if you don't write everything out, you don't have to write it out explicitly, but at least in your head, please think through them this way, because this is really what's important. So you want to make sure that you've got the charges balanced out, and don't just do this little algorithm here. It's not always correct. All right, and our last one is zinc cyanide. Zinc is a transition metal, right? And we don't have anything here to tell us the charge. That would be disconcerting, except that zinc is one of those 4 special cases that we memorized. So we know that zinc is always a +2 ion, and cyanide is a polyatomic ion that we've memorized, and that's Cn-1. So if we want to combine these together, I'm going to go through this a little bit more quickly because I think we've got this. Okay. So if we want to balance the charges, we see that with 1 zinc and 2 cyanides, we can get a positive charge of +2 and a negative charge of -2. So zinc, cyanide, and as before with the ammonium, we don't want to just put a 2 here because that looks like Cn2, like it's 1 carbon and 2 nitrogens, right? So for any polyatomic ion, we'll put this in parentheses, we'll put the 2 down there, and that's the correct formula for zinc cyanide. All right, here's some more of these. I'm not going to work through them in as much detail as I did last time. But what I'd like you to do is hit the pause button, see if you can write formulas for all of these, and then when you're done, unpause. Looks like these are actually a little bit tougher than the ones on the last page now that I look at them. But give them a shot. Try to write formulas for these and then unpause and take a look at what I've got and see if we got the same thing. All right. For the first one, nickel chloride. Nickel is a transition metal, and because we've got the 2 here, we know that it's +2. Chloride, again, it's just a simple anion with a -1 charge. So you can make that table, and if you make the table, you'll see that you need 2 chlorides for every 1 nickel. And so the formula for nickel 2 chloride is NiCl2. Ammonium acetate. Ammonium is polyatomic cation, NH4+. Acetate, polyatomic anion, C2H3O2-. And since this one is +1 and this one is -1, we can combine them just as they are. This one's going to look a little bit odd. There's our formula for ammonium acetate. And this underscores what I've been saying about the need to memorize all of those cations and anions, especially the anions, but cations as well. Because if you weren't really familiar with them, this would just look like a long string of letters, just some crazy combination of nitrogen and hydrogen, carbon and hydrogen and oxygen. And you're like, what in the heck is that? So it's really important to have all of those memorized so that when you see that, you just look at it and instantly say, okay, I see what that is. There's an ammonium over here and there's an acetate over there. This is ammonium acetate, right? It's important that when you look at it, you can immediately see the different parts instead of just seeing one big jumble of letters. All right, lithium hydrogen sulfate. Lithium is a group 1 ion, so that's going to be Li+. Hydrogen sulfate, this is a compound ion. Sulfate is SO4 2-, so hydrogen sulfate is HSO4 1-, and so this is +1, this is -1. We can combine them just as they are. LiHSO4, lithium hydrogen sulfate. Silver phosphate. Silver is a transition metal, and they didn't give us a charge in parentheses here, but silver is one of those special cases. Right? Silver is always +1, so we don't need a Roman numeral there. And then phosphate is one of the polyatomic anions that we've memorized, PO4 3-. So if we're combining these, you can make that little table again. When you make the table, you'll see that you're going to need 3 of these and 1 of those. And so the formula will be Ag3PO4. All right, and our last one, magnesium bromide. Couple parts to this one. Magnesium is just a group 2 cation. Because magnesium is in group 2, we know that it's +2. Bromide, we might not know that one right offhand, but we know that bromate is BrO3, and this ite suffix means that we've moved down 1 step in that oxyanion table, right? So if bromate is BrO3, bromite is BrO2, again with the same charge of -1. Right. So magnesium is +2, bromite is -1, and we can make ourselves that little table. When we do that, we'll see that we need 1 magnesium for a charge of +2 and 2 bromites for a charge of -2. And so magnesium bromite, and again, for polyatomic ions, if we want to indicate more than one of them, we'll use parentheses. We'll write it like that. So that's magnesium bromite. All right, now let's look at going the other direction using formulas and determining the names. In this first one, again, we've got nickel here, a nickel ion, and we've got this oxyanion. So our cation is going to be nickel. This oxyanion, BrO3, is one of the ones that we memorized. So that's bromate. Okay. But because nickel is a transition metal, we have to indicate the charge on the nickel ion here. We can't just call it nickel bromate. We've got to call it nickel 1 bromate or nickel 2 bromate or nickel 3 bromate, whatever that charge is. So in order to figure out the charge in the cation, we need to know what the charge is on the anion. And then we do basically the same thing we did on the previous slides. We just do that same thing backward, right? Okay. So we know that the molecule has to be composed so that the positive and negative charges are equal, right? And bromate has a charge of -1, so that means that the total negative charge is 2, because there are 2 of them here. 2 times -1, which is -2. That means the total positive charge here has to be +2, right? And if we've only got one nickel and the charge is +2, then the charge on that nickel ion has to be +2, right? So this would be nickel 2 bromate. All right. Now we've got a cobalt compound. All right. Cobalt, and our anion here is hydroxide. I often, when I'm writing these, I often capitalize the anion. It's okay if you do that, but technically it's not supposed to be that way. But I'm just kind of, I'm writing things like as if they're titles, or I'm just kind of capitalizing everything. Normally, yeah, normally that should really be written like that. I just kind of like the capitals. Apologize for that. It's non-standard. Okay, so going back to the cobalt hydroxide, the cation is cobalt, the anion is hydroxide, so the name is cobalt hydroxide. But because cobalt is a transition metal, again, just like last time, we have to include that charge in there. So we'll make a little table. According to the formula, we've got 1 cobalt and 2 hydroxides. Hydroxide has a charge, let me put a question mark there. Hydroxide's got a charge of -1, and there are 2 of them, so the total negative charge is -2. That means the total positive charge has got to be +2. And if we've only got 1 cobalt and the total charge is +2, the cobalt must be a cobalt 2+ ion. So we'd call this cobalt 2 hydroxide. All right, and the next one, we've got sodium, and then we've got something that looks a little bit complicated. Right. Here's our cation, and then we have a compound ion here for the anion. Right. Remember That's CO3, 2 minus. It's carbonate. So if we add 1 hydrogen to it, the charge increases by 1, so it goes from -2 to -1. So this HCO3 is a hydrogen carbonate ion. So if we want to write the name for this, we'll write the cation, which is sodium, and the anion, carbonate. Then here, do we need to include the charge on the sodium? In this case, we don't, because sodium is in group 1, so sodium is always going to be +1, so we don't need to include that charge there. In fact, we shouldn't include the charge. It would look really weird if we did. All right. Okay. The next one, we have an iron here, and they've got this big collection of things over here. Right. If you are good at your anions, if you've memorized them, you'll recognize this over here as an acetate ion. So our cation is iron of some type, and our anion is acetate. And if we make a little table, we have a lot of room for a table here. Our iron, don't know what the charge is, we'll call it plus question mark. And our acetate, that. Acetate has a charge of -1, and we have 2 of them. So our total anion charge is -2. Total cation charge is +2. And since we only have 1 iron, it must be an iron 2 ion. So we would write it like that. Okay. All right, and our last one, we've got aluminum and oxygen. And the oxygen here, this is not a polyatomic ion. It's just 3 simple ions, 3 oxides. All right, so we've got aluminum oxide, and we can check the table. We really don't need to in this case because aluminum is one of those special metals that always has the same charge. Aluminum is always 3+, and oxide is 2-. So our total positive charge here is going to be 2 times +3, which is +6. And our negative side is going to be 3 times -2, which is -6. All right. So we've got 2 aluminums for +6, 3 oxides for -6, and all of that balances out. All right. But in this case, we don't need to include the charge for oxygen in Roman numerals because oxygen is one of those special cases. So we'll just name that aluminum oxide. All right. I've got a couple on the next page for you. And let's see. All right. So go ahead and hit pause and work through these. See if you can get the names, and then unpause and we'll look at them together. Okay, so the first one, we got 2 parts. Our cation is a potassium. Our anion is NO2. And you should remember that NO3 is nitrate. And if NO3 is nitrate, remove one oxygen, that means we're going down one step in that oxyanion table. So that becomes nitrite. Right? So our cation is potassium, and our anion is nitrite. And because potassium is in group 1, we don't need to include the charge in the name. So we can just simply call this potassium nitrite. And the next one, we've got chromium for our cation and sulfate for our anion. So our name would be chromium sulfate. Okay. But chromium is a transition metal, so we need to include the charge here. So I'll make a little table. Chromium plus question mark. We don't know what the charge is on the chromium. And sulfate is a charge of 2 minus. So for our anion, we've got 3 sulfates. So the total negative charge is -6. That means the chromium has to have a charge of +6. And if we look at the formula here, there are 2 chromiums. So 2 times whatever that charge is on chromium equals +6. And that means chromium has got to be +3. Okay? So if chromium has a charge of +3, then we want to name this as chromium 3 sulfate. All right. Our next one, our cation here is calcium. Our anion is a compound ion. I think we might have had that one on the last page, right? The cation, calcium, and this compound ion is hydrogen carbonate. Right. And because calcium is in group 2, it's always has a charge of +2. That means we don't need to include the charge here. So we can just name this calcium hydrogen carbonate. And if you want to run the numbers and put them in the table, you'll see calcium is +2, hydrogen carbonate is -1. And so that's why we need 2 hydrogen carbonates for each calcium. All right, our next one, we've got cation is silver. Our anion is this guy over here. ClO4 is not one of the ones that we memorized. But we memorized that ClO3 is chlorate. And so that means if we go up 1 in that table, add an oxygen, then we get perchlorate. Right? So our cation is silver, and our anion is perchlorate. And even though silver is a transition metal, right? Silver is one of those special case elements. The charge on silver is always +1, so we don't need to include the charge here. We don't need Roman numerals. We'll just call it silver perchlorate. All right, and then this last one, again, looks like a big jumble of letters. In fact, I think we just did this one. that's okay. If we look at this, we need to be able to identify the cation and the anion from this jumbly mess. And we see this part on the left, NH4, that is an ammonium ion. And on the right, C2H3O2 is an acetate ion, so that would be ammonium acetate. All right, lovely. All right, so we looked at naming ionic compounds, and two simple rules, really. One is that the name is just name the cation and then name the anion. The only tricky part is you need to name them carefully, right? You need to be able to recognize cations and anions, including all of the polyatomic ones and all of the variants of the oxyanions. And very importantly, you need to remember if your cation is a transition metal, then you need to include that charge in the name. That's part of the name of that cation. Okay, that's an iron 2 cation, not just an iron cation. All right, so that's the first thing, naming the cation and the anion, and that you have to construct them such that the net charge is 0. That's really important. It's really important going both ways, whether you're writing the formula or whether you're determining the name, because sometimes knowing that the net charge is 0 is part of doing the math to figure out what the charge on that transition metal ion was in the first place. All right, so that's important. And you might make a little table like this to figure out how to combine the cations and the anions so that everything balances out. Once you get comfortable enough with it that you feel like you can skip that or do that in your head, that's fine. But I think it's often useful to go ahead and do that and work through it systematically as you're first working on these. And then we use those rules to determine the formulas of ionic compounds based on the name, and going the other direction, figuring out the name of ionic compounds based on the formula. And it's important to be able to do both of those, to be able to go in either direction. And as I said at the beginning, I'll remind you, the whole point of this is so that if you have something like that, it doesn't look like a big jumble of letters, that when you see that, you'll immediately say, okay, I recognize that that compound is ammonium sulfate. It's composed of ammonium ions and sulfate ions, and the behavior of that compound is going to be basically based on the behavior of ammonium and sulfate. Those are the two parts that make up that compound. All right, lovely. This is really important stuff. I know it seems kind of trivial just naming things, but it is really, really, really important. I found in the past that if I give a long final exam, and part of that is nomenclature, students' grades on the entire exam often correlate very well with their scores on the nomenclature section. I think more so than any other section. And I think the reason for that is, this thing right here, right? If you can do well in nomenclature, then you can recognize what things are based on the names, right? We talked early in the semester about understanding how microscopic properties relate to macroscopic properties. This is the same kind of thing, but now we're looking at how the symbolic representations relate to the microscopic representations, and then, of course, how the microscopic representations relate to the macroscopic representations, right? So it's really important that these names aren't just a collection of letters, but they really mean something to you. That's really going to help you in the course, I believe. All right, fantastic. Work on those, and then we'll be back. We've got 2 more bits of nomenclature, both are a little bit shorter. One on nomenclature of acids, and one on very basic organic nomenclature. So we'll be back with those in a little bit.